Okay, in section 10.2, we're going to look at a similar thing that we looked in 10.1 where we compared the difference between two population proportions. In 10.2, we're going to compare two population means. So if we have two means of two different parameters, we're basically looking what happens when I subtract those two parameters. How can I estimate what that difference is? So just like normal, we have to figure out a sampling distribution for this. And the shape of the sampling distribution is normal if both sample sizes are over 30, or of course if it's assumed to be normal. The mean of the sampling distribution for x bar 1 minus x bar 2 is mu1 minus mu2. So we just subtract the two means to get the average. And then the spread, the standard error, the standard deviation of the sampling distribution is given by this formula. This is actually not written correctly on here. The standard error actually should be square root sigma 1 squared, so the standard deviation squared over n1, plus sigma 2 squared over n2. So the squares were missing from that formula on your notes. So that's our standard error. That's how it's spread out. So once you have that, these are population standard deviations. But when we want to make confidence intervals and do significance tests, we can actually use the sample standard deviation in its place. So we'll first look at making confidence intervals where we're trying to estimate the difference between these two parameters. And so similarly to everything we've done, you have to have normal conditions where both are over 30 or it's assumed to be normal. They have to be independent, so one group doesn't really influence the values of the other group. And then finally, we have to figure out the appropriate confidence level and the appropriate degrees of freedom to get that confidence level. Because remember, with means, we typically are looking for t values versus z values. So the formula for a confidence interval of the difference between two means. So we're going to subtract the two sample means, plus or minus t star, which is our critical value, times the standard error formula, which is the square root standard deviations over their sample sizes squared. Now, as far as degrees of freedom, this is pretty important. The degrees of freedom for the t critical value that we'll use our chart for is actually given by a really complicated formula. So the estimate for degrees of freedom is we're just going to take the minimum of the first sample size minus 1 and the second sample size minus 1. That will give you approximately the same degrees of freedom. Now, I will warn you, when you look at your calculator, you'll get a slightly different interval because you'll get a slightly different t-value. That is okay. This is a widely accepted formula to find the degrees of freedom. You can also use a two-sample t-interval function in the TI calculator to get these intervals. So when we get to that point, we can use that calculator function as well. So if by chance you could do the population standard deviation, there is such a thing as the two-sample t interval or z interval. But we'll very rarely use this because we very rarely know sigma. So most times, sigma, which is the population standard deviation, is unknown. So that's when we'll use t. So let's look at an example of how we can make this interval. So the following represents the amount of time it takes calculus students and algebra 1 students to take an exam. So we have some data here. So we have a bunch of calculus students and a bunch of algebra students. And it says assume both come from normally distributed populations, so that's not really an issue. And we want to find the 90% confidence interval for the difference in their means and interpret the results. So in this case, since we have a bunch of data, the first thing I would want to do is find their sample statistics. So for calculus, I'd like to find the sample mean, I'd like to find the sample standard deviation, and I'd like to know how many are in that sample. For algebra 1, I'd like to know their sample mean, their sample standard deviation, and the number in their sample. We'll call this 1 and 2, just for simplicity's sake. So for calculus, their average was 99.67. Standard deviation was 13.45. and we had 9 students. Now, that's not 30, but we already assumed it's normal, so we're not going to worry about that. Algebra 1 had an average of 92.57, standard deviation of much larger, 43.24, and there were 14 in that sample. So if you're going to figure this out, really all you have to do is put it into the formula, which is x bar 1 minus x bar 2. And again, I'm going to assume that this is x1 and this is x2. So any differences would be taking calculus minus algebra. So when we get our results, it'll be important to realize that. Plus or minus t star, which we'll have to find, times the square root of S1, we'll call it S1 squared over N1 plus S2 squared over N2. So we know all these values except for the t value. But I do know my degrees of freedom is going to be 8. Because if I take 1 from 9 and 14, the smaller of those two numbers is 8. So when I look on the t-chart for a t-value with a degree of freedom of 8 for a 90% confidence interval, I'm getting a t-star of 1.860. You should obviously check that for yourself. Make sure your chart says the same thing. It certainly should. So we'll put these values in. So we have 99.67 minus 92.57 plus minus t-star, which is 1.860, times the square root 13.45 squared over 9 plus 43.24 squared over 14. So this is all going to be my margin of error, and so we can calculate and figure out what all that is. So the first part is going to give me just 7.1. So this is 7.1 plus or minus, and then the 1.86 times the standard error is going to give me 23. Let's just go to 1 decimal. We'll say 23.1. So my interval, so we'll have negative 16 to 30.2. So some pretty big differences in the mean. So we are 90% confident that the difference between the two parameters is between these two numbers. But again, the first one is negative, which means the algebra 1 would be bigger, and the second number is positive, so that would mean the first one is bigger, because remember, in this problem, we were doing calculus minus algebra. That's how we did all these problems. So since that one is negative and one is positive, remember that means that we really don't know which one is bigger. All we could really say is with 90% confidence, the difference in the means is between those two numbers. Negative 16 and 30.2, and this in this case would be minutes, because this was all about how long it took to take this test. So that's how we make an interval, nothing too crazy, just following the formula. Biggest thing again, just like for proportions, if they're both negative, then that's a pretty good indication that the first mean is bigger than the second, and vice versa. If both sides are positive, then the first one's probably bigger than the second. Doesn't mean it's a lot bigger, just means it is statistically significant bigger than the other. So hopefully this is pretty straightforward. The second part of our video will deal with how to do significance tests with this same idea. We'll also put up another video where it talks about how we can do this in the calculator. Very similar. You'll see how we get very similar answers, slightly different because of our degrees of freedom, because we use the approximation formula versus the weird formula that really is. So if you have any questions, please let me know.